Continuing our discussion in Chapter 1, I'm going to be starting in Section 1.3 now. We've already discussed Sections 1.1 and 1.2 in the previous video. If you haven't already watched that, now is a good time to go back and do so. In Section 1.3, it's a fairly short section. It talks about random sampling. There are many different ways to go out into the population and sample. Random sampling is the most basic and unbiased way to do so. Random sampling is going to be the first of a few different ways. It's the process of using chance to select individuals from a population that will be included in your sample. If convenience is used to obtain a sample, the results of the survey are meaningless. We try to avoid convenience at all costs. A sample of size n from a population of size big N, so I want you to start to notice some of the letters that are being used here. So a small n is being used from a sample, but a big N is being used for the size from the population. Clearly small n will always be smaller than big N because it's a sample of the population. And it will be obtained through what's called a simple random sampling. A lot of times in my notes you'll see SRS, which stands for simple random sampling. Every time it's possible to get that sample size of n, it has an equally likely chance of occurring. So the sample is called simple random sampling. Steps to obtaining a simple random sample, there are many different ways to do this. One way is to use the number table or graphing calculator or statistical software to generate these numbers. The first one I'll be showing you is the Table 1, which is from the back of the book. Let me pose a question to you. Let's say I want to obtain, let's say I have a room full of 100 people. Actually, that would be the population. And I want to pick out a sample of 5 people from in here. So there are 100 people in a room, and I want to select 5 of them. How do I select those 5 people completely randomly? One way to do that is by using a random number table. In the back of your book, in Appendix A, the very first table, Table 1, is a random number table. So for example, the random number table that is in the back of the book looks like this. You first decide where you want to start in your random number table. So for example, I could start at the upper left-hand corner. I could start anywhere I like. What a lot of people do to keep it completely random is they literally drop their pen and start from wherever it falls. So I'm going to start with the number 31308. So if I start right here, I'm going to list all of the people that fall in under that number. So the first person that will be selected for my sample will be number 31, and I have to use 2 digits because everybody in here is going to be numbered number 0 all the way through number 99. So that's why I'm going to use 2 digits for every single person in my population. So the first person that will be selected will be number 31. The next person to be selected will be number 30. The next person to be selected will be number 80. The next person will be 22, and the last one will be 41. So those 5 people, would be selected for my sample. Now what if you only had, let's say, 59 people in your population, and we started at the exact same place? Well, clearly there is no number 80, so we would just exclude that number and we would go on to the next person. So after 41 comes 01, so we would include 01 in our survey. Another way to do this is using a graphing calculator or statistical software. A graphing calculator, which isn't necessary for the course, but can do the tricks for you as well if you're just interested in learning more about it. So in your graphing calculator, I'm going to use what's called, under the math key, you have a probability function up here. Under the probability function, number 5 is a random interval. So it will give us random numbers given a particular interval that you type in next. So the interval I want to pick is between 0 to 99. And I want to pick the next 5 people within that interval. So when I hit enter, it gives me one random person. Well, the first one would be 0. The next one would be 93, 10, 0 again. 0 got called twice. 54. And then you could keep doing this as many times as you need to until you have the right number of people that are in your sample. Clearly, there are many different apps you can download to your smartphone as well for number generating options. So that was the first type of sampling, which was random sampling. It's based on a computer generating those numbers for you to reduce bias. There are some other effective methods that we will go over now. The first one will be stratified. Remember that the goal of sampling is to obtain as much information as possible about the population at the least cost. There are other sampling techniques that can exist. Stratified sampling. This one is obtained by separating the population into non-overlapping groups called strata, and then we'll obtain a simple random sample from each stratum. The individuals within each stratum should be homogeneous or similar in some way. So for example, an example of stratified sampling, you're going to have a population. Let's say this is my population. And within here, I'm going to separate the population into non-overlapping groups called strata. So let's say this is all Ivy Tech students. That's my population. And within Ivy Tech, we have majors. We have business students. We have nursing students. We have general education students. We have IT students. We have welding students. And I don't know, criminal justice, for example. Clearly, there are many more. But these are non-overlapping because you're in one major or another. Now, I guess supposedly one student could potentially major in 2 different majors, but we're going to pretend that it's not possible and each person is in one major at a time. Each of these individual circles are called strata. So far I've separated this population into 6 strata. Then what we're going to do is we're going to obtain a simple random sample, which is a simple random sample, which we just discussed up above. We're going to take a simple random sample from every strata. So we're going to go into the business. Let's say that there are 500 students in the business degree. We're going to go into that business degree and I'm going to select a random sample of 5 students from the business major. And I do that using the methods we discussed above. Maybe we use table 1 from the back of the book, maybe we use my calculator for random sampling, or we use a computer generated number generator. But we simply randomly select 5 people from this strata, 5 people from this strata, 5 from this strata, 5 from here, 5 from here, and 5 from here. So I'll end up with 30 total in my sample. But I selected 5 from each individual group. The reason why this might be a good option is because you're diversifying on purpose. If we don't diversify, we could end up with all of our sample from one particular major, and we're not getting the opinions and feelings of those from other majors. So sometimes a stratified sample is a better use of a random sampling because you're forcing diversity to occur. Another example of sampling would be what's called a systematic sampling. A systematic sampling would consist of selecting every kth individual from a particular group. So if we wanted to select every certain number of person from a group, any number between 1 and k would be an integer. So first determine how many are total in your population and determine what your desired sample size will be. So for example, if our population size is 1,000 and I want to select 15 people from the 1,000. First we compute n divided by n. So in my calculator, I would do n divided by n, and I get 66.66. And it says round down to the nearest integer. So k is 66. Then randomly select a number between 1 and k. We'll call it p. So we're going to randomly select a number between 1 and 66. So I'm even going to let my calculator do that for me, so it is really random. So I want a number between 1 and 66, and I got the number 1. Let's go with 28 instead of using the first number 1. So the first number I select randomly is the number 28, and we're going to call this p. So p is 28. So the sample will consist of the following individuals. If I numbered all of these people 1 through 1,000, I'm going to start at the 28th person instead of the first. I'm going to start at the 28th person in this list, and then I'm going to add k to that. So then I'm going to add 66. So the next number I'm going to do is add 66. So the next number will be 94. Now if I add 66 to that, the next person I will call will be 160. And then I keep doing this until I get up to near 1,000. So obviously I've went too far. So the last person in my list would be number 952. And all of those added together would give me the right number of people in my sample. All of these people would be 15 individuals. The third type, actually the fourth type, the first type was system random sampling. Then the second type was stratified. The third type was systematic. The fourth type is cluster. In a cluster sample, it's very similar to the stratified. So pay close attention. This is obtained by selecting all the individuals within a randomly collected group of individuals. So let me go back to the picture that I drew for you just a second ago, which was for the stratified. This was the stratified example, where we separated into groups and then we took a random sample from each group. Now, in orange, I'm going to show you how a cluster is going to look different. A cluster sample, you select all the individuals in one selection group or collection. So let's say I separated Ivy Tech into these majors. A cluster sample would select every single individual within one particular group. So let's say I took all of the IT, and every single person in here would be part of my sample. And let's say there were 56 people in IT, and I've taken every single person from IT and used those as my cluster sample. So I didn't survey anybody in nursing, business, general studies, welding, or criminal justice, just everybody in IT. So we're not diversifying. Here the goal would be if we specifically want to ask a question to only a specific type of a person. They probably have something in common. In this particular experience, it would be their major. So this is quite different than the stratified, where you're trying to diversify, where cluster, you're trying to survey only those that have those clustered characteristics in common. Here's a picture of the different types that we've discussed already. The simple random, you're basically just finding different numbers within a number generating table. Stratified, we separate them into two groups, or called strata, and then we simple random sample a few from each group. Cluster is different. We take all of these people, we separate them into clusters. And then we take everybody from one cluster, and you could take multiple clusters, but you're taking everybody within that cluster for part of your sample, instead of a sample from each individual group. Systematic says we take every kth person. If K is 3, for example, we would take every third person. So if we start at 2, and then we go to 5, 8, 11, and so on, and so on. You're taking they're spaced 3 apart. The last example is a convenience sample, and this should be used as a last resort. It's one in which the individuals of the sample are easily obtained. So if I'm standing at the front doors of the Ivy Tech and I ask every single person that comes in over the next 15 minutes to take a survey that would be convenience, there would be a lot of bias, potential bias within convenience sampling, because you're only asking people at that particular door within that particular time frame what their opinions are about your sample. In practice, most large-scale surveys from big companies, they obtain samples using a combination of these techniques that were just presented, and that would be called multi-stage sampling. In fact, when we talked about the stratified sampling, you'll notice that we use simple random sampling within the strata. So that was multi-stage within itself. So now I'd like to talk a little bit about bias within each of those typical samplings. In bias sampling, you're going to notice that there are 3 different types. The first one is sampling bias. This means that the technique that is used to obtain the individuals in the sample tends to favor one part of the population over another. You'll find that you'll have undercoverage within a sampling bias, and that occurs when the proportion of one segment of the population in a lower sample than in another. You want to try to get the coverage the same for all different types of groups. Then there's non-response bias. This exists when individuals selected in a sample do not respond from different opinions. You'll usually find those that respond to a survey are ones that have high opinions, usually negative, sometimes positive. But if they don't really have an opinion, then they're not going to respond. And non-response bias is also considered a bias. This can be improved through the use of calling them back or giving them rewards or incentives if they do reply. Then you actually have response bias. This exists when the answers on the survey do not reflect the true feelings of the respondent. So if I have a particular feeling about whether you should put a park near my house, but those particular feelings aren't one of the multiple choice answers, well then you're going to get an answer based on one of the results that were there, but wasn't my true feelings to begin with. To prevent this, you want to make sure the interviewer who's asking the questions doesn't produce any errors. The interviewer should not misrepresent any of the answers and use their own judgment for what the interviewee was actually meaning in their explanation. Be careful with the words that are used in the survey question so they're not leading the interviewee down a road of potential bias. And then make sure the order of the questions within the actual survey are randomly ordered, so they don't lead you into a particular opinion by building on a topic. There's also what are called non-sampling errors and sampling errors. Non-sampling errors are errors that result from a sampling bias, a non-response bias, or a response bias, basically all the ones we talked about up here above, or even a data entry error, which can commonly occur. Such errors could also be present in a complete census of the population. A sampling error is an error that results using a sample to estimate the information about a population, which we're going to do a lot of in this course. This type of error occurs because the sample is always going to give incomplete information about the population because you didn't ask everybody. It's virtually impossible to ask everybody in a population what their opinions are. So we'll take a smaller sample and infer that they're probably pretty close to what the population is, but the error in between those two values is what's called the sampling error. In section 1.6, we'll be discussing the design of experiments. An experiment, remember, is a controlled study that is conducted to determine the effect of varying one or more explanatory variables or factors, and it has a response. Any combination of these values of these factors is called what's called a treatment. The experimental unit or the subject is the person or object or some other well-defined item in which the treatment is applied. A control group serves as the baseline treatment that can be used to compare other treatments. A placebo is an innocuous medication such as a sugar tablet. It looks and tastes and smells like the experimental medication. The reason why a lot of experiments will use placebos for the control group is so that psychologically they don't produce symptoms that didn't really exist. Blinding refers to non-disclosure of the treatment. There can be a single blind experiment where the experimental unit or the subject does not know which treatment they're receiving. So if you have a bunch of patients and you give some a placebo and you give some an actual vaccine, they are single blind. In other words, they don't know whether they received the sugar pill or whether they received the actual drug for the treatment. They're single blind, meaning they don't know what they received, but you as the experimenter or the researcher does know. But double blind would mean that neither the experimental unit nor the researcher knows. Sometimes this is important in case the researcher can invoke their own bias into seeing potential symptoms that may not exist. Let's look over some examples. Let's say that the English department of a community college is considering adopting an online version of the freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half of them receive the traditional face-to-face course, and the other half give online. At the end of the semester, both groups are given a test and will determine who did better. So who are the experimental units? This is a good time to pause the video and see if you can answer these yourself, and then unpause the video to check your answers. The experimental units in this case will be the students in the class. What is the population for which the study applies? Well, it will be all freshman English students. At this particular community college. What are the treatments? Well, half of the English class are going to get the traditional face-to-face instruction, and the other half are going to get online instruction. The response is going to be their exam scores at the end of the semester. And then we'll be able to determine which group did better or if there was a difference at all. So they're going to be taking the exact same exam. Why can't this experiment be constructed without blinding? Well, it can't be, the experimentees cannot be blinded because clearly they're going to know whether they're coming to class or not. So whether they're coming to class, they know that they're traditional. If they're sitting at home, they know that they're online. So in this case, it would be impossible to blind the students because they know which type of class they're in via the instruction that they're receiving. So both students and instructors know what treatment they're receiving. To design an experiment, it means to describe the overall plan in conducting the experiment. There are 6 main types to designing an experiment. First, identify the problem. Determine the factors that affect the response variable, such as exam scores. Determine the number of units that you'll be using, such as the number of students in your class. Determine the level of each factor. Conduct the experiment, and then test the claim. So we're going to go through a couple of examples of designing an experiment. A completely randomized design is one in which the experimental unit is randomly assigned to a treatment. This is the simplest type of experiment. So this is a completely randomized design. There will be another type of design on the next page in a moment. So let's talk about this randomized design. Let's say the octane of fuel is a measure of its resistance and detonation with a higher number indicating the higher resistance. An engineer wants to know whether the level of the octane in the gasoline affects gas mileage of an automobile. Assist the engineer in designing this experiment. Again, this is a good time to pause. The response variable here is miles per gallon. That is what we are measuring. At the end of the experiment, we're trying to measure the gas mileage, and we're comparing gas mileage from vehicle to vehicle to see whether octane played a role. What are the factors that affect miles per gallon? Well, obviously engine size, temperatures outside, road conditions, driving style, and other car characteristics. You may have come up with some other ones. But there are different things that affect the miles per gallon. What are the experimental units? Well, let's say it didn't really specify, but let's say we use 12 cars of all the same model and same year. So if they're all the same, that will eliminate any changes that we have on, for example, engine size and car characteristics. Will eliminate those as being variables if we use all the same cars. List all the variables and their levels. Well, let's see, the octane of the gas, that's one variable, and that will come in 87, 89, and 92. That's based on price. The engine size, well, we fixed that. Temperature and conditions, well, we can fix that too. As long as we go out the same day, the temperature and conditions will be the same for each of our vehicles. So we can fix that as well. But we must make sure we do the experiment all in one day while the temperature conditions are constant. Driving style, well, we can fix that too. And we would fix that as long as the same driver is driving each of the vehicles. So that also can be fixed. So we really only have one variable together, which is the gas. We're trying to eliminate all of these factors so that way we don't have confounding. We only want one variable to change whether the miles per gallon is being affected. So now we're ready to conduct the experiment. So we're going to randomly assign if we divide all 12 of these cars among 3 different octanes, let's assign 4 cars to each octane. So in other words, 4 cars will have 87 gas, 4 cars will have 89, and 4 cars will have 92. Then we'll drive until we are out of gas. Then we can compute how many miles per gallon we used. So the claim that we are testing is whether or not octane levels have an effect on miles per gallon. So you see what we did here. We really tried to isolate just the variable that we wanted to measure by fixing all of the other variables that could potentially change the miles per gallon. Let's do one more example. Again, this was an example of a completely randomized design where each experimental unit is just randomly assigned to a treatment. We took 4 random cars and we randomly assigned each of those 4 cars to each of those gas levels. The last type of design is what's called a matched pairs design. This is also an experiment. This is the second type of experiment. And in a matched pairs design, it's going to be an experimental design in which the experimental units are paired up. The pairs will be matched up so that they are somehow related. Sometimes it's a person before and after a treatment. It could be twins. It could be a husband and a wife. It could be 2 people from the same geographical location, and so on. In other words, they will be paired up based on a characteristic that they have in common. There are only 2 levels of measurement in a matched pairs design. For example, xylitol has proven effective in preventing dental cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each of these. The researchers then measured the children's ratings of the 2 types of milk. Now notice, cavities really had nothing to do with this question. What we were doing is giving children milk with or without the xylitol in the milk. We asked them just simply to evaluate the taste. So the response in this case is the taste. Maybe it was a rating, maybe for the children we rated it from good, middle to bad, or maybe it was a 1 through 5 sliding scale. Think of some of the factors in the study and which ones can be controlled and which ones are going to be manipulated. Okay? Things we can control. The ages of the individuals, we can control what ages are taking the actual milk taste ratings. We can control the gender, and we can control their taste preferences. The only thing that we're going to manipulate is the milk. It's the only thing we want to change here. We're going to give them milk with and without xylitol, but the other things that are controlled are the ages and genders and their taste preferences for each of those individual people. The treatments themselves is the milk. There are 2 treatments. Half the students will get the milk without the xylitol, and the other half of the children will receive the milk with the xylitol. Now this is a matched pairs design. And the reason that this is a matched pairs design is because it wouldn't make any sense. Let's say here's me and here's you, for example. Okay? And I tried milk. I tried 2 different types of milk, and well, so did you. So let's say I liked the milk with the xylitol, but I didn't like the milk without. So I'm comparing my taste buds with my taste buds. I'm controlling that. I want the age to be the same, the gender, and the taste preferences to be the same between my 2 cups of milk. Same thing for you. What if you didn't like the xylitol? You know what, but you didn't like milk either because you don't like milk by itself. So it wouldn't make any sense to compare your taste buds for milk with my taste buds for milk with xylitol because we have 2 completely sets of taste buds. We want to try to control the taste bud preferences. So how we control that is we compare just my likings to each other. All I'm doing is comparing this. I want to compare what I liked to what I didn't like within just myself as being a matched pairs design. And then I'll compare your 2 cups of milk. But I will not cross compare between you to me based on taste preferences. That wouldn't make sense. So this is an example of a matched pairs design. We are going to use this matched pairs design to use 75 Peruvian kids. Those will be our experimental units. So we're really going to have 150 total responses because each person will have 2 responses, one for each cup of milk. So for each of the 75 kids, they'll have 2 responses or a total of 150 recordings that we have to take down in our logbook. So why would it be a good idea to randomly assign whether the child drinks the milk with xylitol first or second? Well, drinking order can affect their liking. So what if the xylitol tastes bad and you give that to them first? Well, then they're probably not going to like the milk either because they're going to think it's the same thing. So you really want to randomly assign which cup they get first. And this will remove any effect due to drinking order. Do you think it would be a good idea to be double blind? Most definitely. Certainly single blind because we definitely don't want to tell the children which one has the drug in it because they're immediately going to give us a frown face if we told them. So certainly single blind makes sense. But also it might make sense to have the researcher also be double blind in this experiment. And the reason being is because if we're going off just facial expressions, if the student or the child gives a frown face, it could just, based on the researcher, might look at that frown face as being something bad, but maybe they're just being goofy. So we really want to make sure that at least it's single blind, but maybe even double blind as well, so that way we don't read something into each of these children that wasn't really there as a symptom.